Alright, thanks for watching, and today is a very exciting episode as usual because I want to present you some cool probability paradoxes. Because that's the cool thing about probability, it's very paradoxical and it teaches us a little bit about how we think. So it's a little bit of psychology here as well. First example I want to show you, and I think I'll do 4, is a very nice thing called the St. Petersburg paradox. And consider the following game. And it's a game that's played in stages, and at each stage we toss a coin that comes out head or tails. So you start with $2. Okay, so start with $2. And at each stage, every time a head appears, you double it. Okay. And if a tail appears, then you stop. You stop and you go away with the money you have. So stop and go. So let me illustrate. Suppose, again, you have $2, we toss the coin and it comes out tails, then you lose and you just go away with $2. And suppose you have the following. You toss the coin, hey, it's heads, so you double your amount. And then it's tails, sorry, you lose, then you go away with $4. Or euros or whatever, ruble, I guess would be better, because St. Petersburg. And now, let's again, you play it again. So you first toss it, great, it's heads, so times 2. Then it's heads again, well, lucky you, and then it's tails. Then you walk away with $8. And similarly, okay? And the question is, how much would you be willing to bet for that game? Would you be willing to bet $10? $20? In fact, I'm claiming that you should bet your whole life savings on this because on average, you will get infinitely many dollars from that game. And let me explain you why. It has to do with expectations, and basically the definition of expectation is for every event, you multiply your gain by the probability of getting that gain. So gain basically has to do with random variables, but suppose you have a game, okay? And the probability of getting the gain x1 is p1, the probability of getting the gain x2 is p2, etc., etc. Then the expected value is p1x1 plus p2x2 plus p3x3, etc., etc. So always you gain by the times the probability of getting that gain. And so let's do it in this case. So first of all, what is the probability of getting $2? That's if the coin lands tails, which is 1/2. So there's a 1/2 chance of getting tails. Then, what is the probability of getting $4? Well, that's if you have exactly the scenario heads and tails, whose probability is 1/4, because there are 4 choices: heads, 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 tails, tails, heads, and tails, tails. So 4 times 1/4. What is the probability of getting $8? So if the gain is $8, what's the probability? Well, it's 1/2 times 1/2 times 1/2 plus 1/8. So 1/8, etc., etc. So the expected value, or the average value of this game, is 1 plus 1 plus 1 plus 1 plus dot dot dot, which is infinity. So, if you play this game, in average you will get infinitely many dollars. The question is, why don't people bet infinite, any amount of money for this? It's because you're all fools. Because you should play, bet infinitely many dollars. But I was reading about this. It's a bit has to do with economics. It's because sort of happiness, it's not decreasing linearly. It's like concave down. So, for example, if you have $1, if your savings is $1, and I give you an extra dollar, then that's a lot. You're super happy, you drink a Coke or something, whatever you can afford for $1. But let's say you have $1 million, and I give you an extra dollar, then that is nothing for you. It's like there's a decreasing marginal utility of money here. And so because, let's say you, even though on average you get infinitely many dollars, it's too risky for you to invest in that thing, to bet $1 million for that. So that's right. It's not the math is correct, it's just the way we're thinking is not quite correct. Okay, so that was the first paradox, St. Petersburg paradox. And by the way, in Soviet Russia, value expects you, because we have the expected value. Okay, anyway, the second thing, it's more of a game theory paradox, but it's still pretty cool. It's something called Paranhos paradox. So example 2. Paradox. And it says the following. It turns out basically there exist two games that if you play them separately, you will lose for sure, but somehow if you combine them, you can win. So let me write that down. So fact, there are two games such that when played independently, you lose for sure, but when but when combined, you win for sure. Pretty shocking. Okay. And it also tells you it's good to cooperate or to mix and match things, so you win for sure. The question is, what are those games? So, first game is my favorite game. I just take $1 from you every time you play that game. So I just take $1 from you. Pretty sketchy game, but apparently there are also more sophisticated examples. So there are games you would want to play that, makes this work. And game B, that's also really cool. If you have an even number of dollars, of currency or dollars, you win $3, else you lose $1. No, worse, $5. Let's make it even sizzlier, but that also works, okay? So it's cool. It's like I ask you, hey, what's up? How much money you have? If you have $100, I give you $3. But if you have $99, unfortunately, you lose $5. And I'm claiming that, well, first of all, obviously in game A, you always lose, okay? So that's no questions asked. And I'm telling you, in fact, for game B, you eventually lose as well, because suppose you do it as follows. Suppose you play game B, Well, you start with $100. Yay, it's even. So it's 103. Boo, it's odd. So you lose $5, 98. Yay, it's even. So you win 101. And then boo, it's odd. So it's 96. Yay, it's even, 99. Boo, it's odd, 94, etc., etc. So you can sort of see your money slowly disappearing. So it goes like up, down, up, down, up, down. So I'm telling you, for game B, you'll also eventually lose. So it's not good just to play game B. But you can somehow combine those two games to actually win money. Namely, just alternate B and A. But if you play ba 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 ba, oh, ba ba, no, babar, that was the elephant. Okay, no, ba 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 ba, then you win for sure. For sure. So, for example, let me illustrate. Here's why. Suppose you play with $100, so you start with $100. Okay, great, it's even. So you win 103. But then you don't want to lose $5, so play game A. So it's a little risk to take. And you get $102. Great. Since it's even with B, you gain $3, so 105. And again, you don't want to risk losing $5, so you play game A again, 104, and then you play game B, etc., etc. So here, eventually, you will win money. And it's sort of paradoxical, but it is true. You know? So that's why it's actually altruism is pretty good. Okay. All right. So that was Parrondo's paradox. And now I want to move on to another kind of cute scenario. It's what's called the exchange problem. And that's for people like me who are completely indecisive, okay? And this problem just makes me cry. So exchange paradox. So suppose you have two envelopes. So this is envelope A and envelope B. I'm claiming, weird envelopes, but anyway, I'm claiming you can never make a choice of which envelope to pick. And again, each envelope has money, and suppose this envelope has X amount of dollars, and I'm telling you, you could choose envelope A, or if you choose envelope B, you either have double the amount or half the amount. And I won't really tell you. So the amounts are either x over 2 or 2x. And the question is, and I'm claiming, in fact, in terms of expected values, it's actually better to switch to the other one. Because what is the expected value here? With a probability of 1/2, you get x over 2. So 1/2 of x over 2. And with probability 1/2, you get 2x. And if you calculate that, you actually get 5x over 4. So on average, you actually win, like x over 4 amount of money. So in fact, it might be better to switch to B. That said, so suppose now he's like, okay, well, let me pick envelope B. But then we can do the same thing. Suppose you have Y, right? Either you pick the wrong envelope and the winnings here are 2Y, or you pick the correct envelope, which means here your winnings are Y over 2. And so in this case, the expected value is 1/2 times 2Y plus 1/2 times Y over 2, which is 5Y over 4. So in fact, if you have envelope B, it's actually better to switch over to envelope A. But then at envelope A, you have the same issue where it's better to switch around. And so basically, you can never make up your mind. And you're like, oh my God, why? I know I'm sometimes like, when I'm at the restaurant, I look at the menu, I'm like, I don't know. The left page looks tasty, but the right page looks tastier. And then I'm like, on the right page, I'm like, the left page looks better. And luckily though, there is a solution to this problem. It's just to think of the problem in a different way. So instead of thinking, hey, you have X dollars and you might win 2X dollars or get X over $2, think about it more as, someone sort of pessimist or something, saying, well, I don't really have X dollars, I take it for granted. Let's say I have $0, and by switching, I could either be happy and get X dollars, or I could be unhappy and get minus X dollars. Because that's sort of how we think about winning and losing. And in this case, the problem is resolved because the expected value is 1/2 times X plus 1/2 times minus X. And in that case, the expected value is in fact 0, and and you have to make your own decision. Sorry, but the math doesn't really help you. Alright, so that's also a neat thing called the exchange paradox. Again, horrible for indecisive people like me. And lastly, I want to talk a bit about random walks. And here's a very surprising result, I have to say. And let's first do a random walk in one dimension. So suppose you're an ant walking on the real line, a sort of more of a drunken ant, where you start at 0 and you just walk randomly like this, and you don't really know where you're going really. And the question is, suppose you start at 0, what is the probability that you eventually go back to 0? The probability of eventually going back to 0. And it turns out in one dimension, the answer is 1. So for sure, you return back to the origin. The probability is 1, and it makes sense because how can you not go back to the origin? It means, for example, you start here and you just eventually go to the right. And it's very unlikely that you make so many steps to the right that you don't go back to the origin. So that's in one dimension. And now, suppose instead you are a drunk person in 2 dimensions. So suppose this is R2. And you start at 0, 0. Suppose your home is 0, 0, and you just do a random walk like this. The question is, what is the probability that you eventually return to 0, 0? And guess what? The probability is 1. So even if you're drunk, if you start at home, eventually, if you take an infinite, maybe a long amount of time, you actually go back to 0. Pretty cool. But now, suppose that you're in 3 dimensions now. And you start at the origin. So suppose now you're a drunk bird, and you do a random walk. Okay. So this is R3. The question is, what is the probability that if you start at 0, you eventually go back to 0? And yes, it's it's a paradox. But fact is, the probability is strictly less than 1. I believe it's 2/3 or something. So in 3 dimensions, if you do a random walk, you don't necessarily go back home. And to conclude this probability paradox adventure, I want to end with a quote by Kakutani, who, which illustrates this process. He said that a drunken man will eventually find his way home, but a drunken bird may get lost forever. All right, so if you like this little paradoxical probability session and want to see more math, please make sure to subscribe to my channel. Thank you very much.